Hi, everybody. Okay, so we're going to get started pretty quick here. So welcome to the 102 sensor training. This is going to be an overview of all the sensors, of the sensor and some of the capabilities of the sensor. We'll be going more in depth on the on-site training, but this will give you a pretty good overview of what everything is or how the sensor works. Again, following the same format as last time, we're going to open up questions partway through every few slides just to see if there's any questions. But during the actual presentation, we'll have everybody on mute. All right. I guess I don't know if we're waiting for. We're still waiting for another few more people, but we'll get started and they can just hop on when they get here. All right. I'm going to hand it over to Tim. Tim is the VP of Hardware and RF Engineering, and he's going to be the one doing this presentation. So if you have any questions, direct it to him, and we'll be good to go. All right, Tim, it's all yours.
All right, thanks, Vic, for that gracious introduction. So my name is Tim Thompson. I'm the I'm the VP of Hardware and RF Engineering up here in Picton, Canada. We're based out of the Coquitlam office, which is just a suburb of Vancouver, if you know where Vancouver is. And nobody can seem to pronounce the name, so I've got a little bit of a phonics there for Coquitlam. So Coquitlam is where we are, and let's get going. So I've got a little bit of an outline here. We're going to start off with a bit of a system overview, maybe a bit of a review of what Vic has already talked to you about. Then we're going to get into the sensor. Going to talk briefly about the firmware on the units. Then we'll get into a little bit more detail on the detection capabilities and limitations, followed by some RF propagation information, which I feel is very important to know. Antennas, power, and then how the data is connected to the unit. So based on some of the stuff that you probably heard from Vic last week, I borrowed this slide from Woz Huerdijn, who's the VP of Products, as a representation of how the system really comes together. So we have, potentially have multiple sites, each with multiple sensors, and then the multiple sensors that are then connected to one or more RSCs at each site. There's RSC1 and RSC2. RSC2 is for redundancy if there's any problem with RSC1. Everything out of the RSCs basically do all of the local processing of sensor data, and then that goes up into the cloud where it goes back to the back end for all the data analytics and that sort of thing.
Tim,
your screen is not being shared.
Just for information, I do not see your screen.
Yeah, your screen is not being presented right now.
Okay, that'd be Vic's fault. I'm letting him drive the go-to meeting.
All right.
Can you see now, Trish?
Yes, sir. I can. Yes.
Okay.
And yeah, now I can again.
All right, Vic's just finishing off playing with things here.
Apologies.
All right, so we went through that one. System overview. I'll leave that slide up there for a little bit longer so you guys can take that in. So obviously we have, each site has the potential for multiple sensors. As you know, the sensors are then spread out across the site in some sort of grid-like format, potentially on multiple floors. And all the data from every sensor goes back to the RSC where it's processed, and the information from each sensor is then, Vic's reminding me what the RSC is. It's the remote sensor controller, for those of you that don't know. And that has all the code in it to basically talk to the sensors. It uses the APIs that have been defined in the firmware to both configure and extract data from the sensors.
Yeah. Physically, what does it look like?
Sorry, just Yeah, Vic's doing some more stuff right here. We'll take some questions a little later. I guess there's new people added today.
Yeah.
And Vic's taking the mouse again from me. Jeez.
Apologies. There you go.
All right, so this slide shows the 4000 SE sensor, which I'm sure you've all seen in one form or another. It's been around for about a year now. It is the flagship sensor that we have right now, and I believe everything else has been deprecated, and we're not supposed to be selling any of the 3000 series anymore. Some of the key features of the device are obviously cellular detection. We detect GSM, CDMA, WCDMA, IDEN, and LTE signals. On the Wi-Fi side, you can see we detect BG, A, and N, so it is a dual band device that we have in there, both 2.4 and 5 gigahertz. Right now, with the 4000 SE, we detect up to version 4 of Bluetooth. Version 5 is obviously fairly new, and at this point we actually do detect most of version 5 except for some of the new high-speed modes, which we are looking at how to include those in the current system. The other big features of the 4000 SE are the daisy chaining installation support, where you can daisy chain up to 4 units together. That allows you to reduce your installation costs by running basically one cable rather than 4. Obviously we have PoE support as well, so we support both 802.3 AF, but only in the single ended mode, non-daisy chaining mode. In daisy chaining mode, we support PoE passively. So passive PoE works in daisy chain mode. Obviously, now we've gone from the external antennas on the previous generation to internal antennas. Some of our customers were really asking for those kinds of aesthetic changes to the enclosure, and so we've provided that. Later on, you'll see how we have hidden some of the cable in behind. There's what's called a dog box in behind where all the cables plug into, and that allows you to hide everything in behind and potentially over something like a junction box. There are also international and domestic versions, depending on which regulatory domain you're going to be wanting to operate in. So the international versions are basically for everywhere outside of the US and Canada. There are some unique instances around the world where some countries like Australia have allocated the bands in a very odd kind of way. So there's always exceptions to the rule, but for the most part, the domestic is North America, US, Canada, and international is the rest of the world. And the main difference between those is strictly on the cell board, where there's some filtering that goes on to determine which frequencies it listens to. So based on the, basically the cell sensor board is its own little standalone board, which supports the frequency bands as shown in this particular slide. There are more frequencies that it could support with changes to the firmware itself. Basically, we have to update the firmware with new bands as we start adding them. Now, during the manufacturing process as well, we also only calibrate for a specific number of bands. So as we add more, then we have to change the calibration process at the factory as well. So the differences between the North American version, the domestic version, and the international version are basically the cellular frequencies that are supported. Fundamentally, it's on the GSM side. GSM bands are basically filtered through some what are called SAW filters on the board, and they allow the different frequencies to go to the different receivers correctly. So on the North American side, we do GSM, CDMA, WCDMA, and IDEN. And LTE is almost there. I forgot to put it on this particular slide. But in the international side of things, there is no CDMA, so obviously we don't need to support it there. I wanted to go a little bit into the actual architecture of the internals of the 4000 SE at a pretty high level. There's a number of building blocks within the 4000 SE. There are 5 antennas. There's a main processor board, the host board, which is from a company called Compex. And that host board does the main processing as well as the communications, as well as handles all the power for the system. It handles the PoE, handles the Ethernet in and out, and that sort of thing. Also on that Compex board are 2 mini PCI slots, which are filled, at least one is filled with another Compex 802.11 ABGN board. Now one board will be used for detection, and optionally we can add a second board to create a mesh backhaul network. So the Compex board primarily does that. There's a cell sensor board. The cell sensor board is really the main host for detecting, obviously, all the cellular detection stuff, as well as any other spectrum that we want to detect. It basically consists of 4 receivers, 4 discrete receivers, 2 narrowband scanning receivers, and 2 wideband receivers, which are, basically look at a very wide chunk of the frequency spectrum, and then listen for strong signals in that frequency spectrum and lock to them. The cell board also includes a relatively low power MCU, the microcontroller unit. That microcontroller unit then takes all the data from the receivers. It controls the receivers, it gets the data from the receivers, and then acts as the communications interface over the serial port to the Compex board, which then handles the push of the data back up to zone defense and the RSCs and so on. There's also the Ubertooth board, which does the Bluetooth detection. As we said before, the Bluetooth handles up to version 4 right now, and that's basically a plug-in USB dongle that plugs directly into the Compex board. So fundamentally, everything is routed through the Compex board. The Compex board does the channel allocation for all the Wi-Fi detection. The cell sensor board is also set up with various scanning profiles that are all controlled through various APIs that have been created. There are, as I said before, there's multiple antennas on there. There's multiple antennas for the cell board. There's 2 broadband cellular antennas for the cell board that cover from roughly 700 megahertz to 3 gigahertz, I believe. So we've got a lot of expansion capability there as we want to move into different frequencies. There's a Bluetooth antenna, and then dual band Wi-Fi antennas. If the mesh card is not present, then both antennas are plugged into the single card for detection to improve its ability, basically by adding some spatial diversity. You'll also notice there's 2 gigabit Ethernet ports on that device on the Compex board, and those are externally available. One port is master, the other port is the slave. So basically you plug into master, and then if you want to daisy chain, then you plug the next one into the slave port, and so on. All right. A couple little things for nomenclature here as we get into more of the details with the sensor. RSSI being the receive signal strength indicator, which is basically how strong the signal is once it gets to the receiver. And dBm, which is decibels relative to a milliwatt. I don't know how many of you are familiar with decibels or dBm, but they're quite important in some of the stuff we'll be talking about, and certainly we'll be going over it in much more detail in the on-site training later on. I'm going to talk a little bit about the firmware here. So the sensor itself contains a lot of firmware in it that's been, some of it's completely custom, others of it has been, some of it's semi-custom but off the shelf. Right now the host board runs a modified version of an embedded Linux called OpenWRT, and that, as I said before, is responsible for all the communications, running the Wi-Fi, doing some Bluetooth analysis, the pass-through communications from the cell sensor board all goes through the host board firmware, which all runs this OpenWRT version of Linux. The cell sensor board also in its microcontroller has a small real-time OS, and that basically does all the command and control for all the different receivers, as well as implements the communications pathway to the host board. The Bluetooth detector, obviously that also runs some embedded firmware, and all of the firmware that we have is upgradable through ZD, through APIs that have been written over the number of years that we've been working on this project. I won't go into too much further detail about the firmware, probably will in the on-site training later on.
I think this is a good time to pause for some questions. I'm just going to open up the volume for some questions. If anybody has any questions, speak now. Are there any questions out there?
I've got one.
Fire away.
Go ahead.
Okay, sorry, I just wanted to make sure you could hear me all right. This is Brandon Lanford. I recall being on site with a deployment last year with the 4000 SEs when they were brand new.
Yep.
And we had some difficulty. This is unrelated to wireless detection, but it just comes down to functionality and usability of the device.
Right.
We had some difficulty beyond 150 or 170 so feet with wired connections using PoE. We weren't able to auto-negotiate at a gigabit to the 4000 SEs. We had to use statically configured 100 meg links in order for it to be reliable.
Right.
So I wondered if there was any discussion around replacing or upgrading the the gigabit chip or gigabit ASIC on the board.
Not on that particular board. The Compex board that we're currently using is fundamentally EOL, end of life. So the next sensor that comes out will be completely new and different to this one. But there's no plans to upgrade that chip at this point in time. One of the issues is the PoE pass-through may be affecting, and the daisy chaining may be affecting some of its capabilities. But I don't know, were we able to reproduce some of that stuff here, Vic?
Yeah, we've had actually pretty good results on the daisy chaining here up to 150 feet. We weren't having very many issues with the Cisco switch, I believe is the one that we got.
Yeah.
But we were able to reproduce the issue, and then we were able to kind of figure it out once we did some playing around with the Cisco switch.
Yeah. Yeah, so, going forward, we will be addressing that, but not on this particular platform, unless we get some different direction from the higher-ups.
Of course.
Yeah, so we do know that's a problem. We have run into that with other customers as well, and yeah, the fallback to 10100 is the recommended approach right now.
Great. All right, thanks.
Hey, can you hear me?
Yep.
Okay, this is Joe Mycene. I got a couple of quick ones for you, kind of related. So, what is the what's the limiting factor on the daisy chaining to 4 sensors?
Power and data. So the injector is typically around 30 watts, and each unit takes about 7.5 watts. So, you know,
Okay.
if you do the math, it adds up real quick.
Okay. No. Okay. No, that's fair. Good. And right now, is it my understanding that we can or cannot integrate the 4000 SE wirelessly?
Not yet, no.
Not yet. And where is that on the roadmap?
You're talking about the mesh backhaul?
Yes.
Yeah. It's currently in development. We're doing the alpha release for it right now, so it's in software development right now. But that's just alpha. We got a lot more testing to do before we're going to be releasing that.
Okay, because I'm thinking about the RDS kit, or I should say the newer version of it.
The PSK kit, yeah, that's fundamentally what we're targeting for the alpha, or for the Mesh 2.0 as we're calling it. And yeah, that's what we're testing right now.
Right.
But that will be available.
Okay, and then finally, moving to the. Okay.
Yeah, but so when the PSK
available when? I'm sorry.
So when the PSK is available, then the Mesh 2.0 is available for at least the PSK.
Okay, and then last question I had: when you move from the external antennas to the internal antennas, any change in sensing range, one way or the other?
Not necessarily sensing range, but the overall radiation pattern of the antennas has degraded slightly. So we are experiencing a few more issues that way.
Okay, and is that a 10%, 5% degrade?
I don't have those numbers on top of my head right now.
Okay, all right.
Yeah.
All right, thank you for your questions. We're just going to move on just to try and get some more information in here. We'll be putting everybody on mute again. Thank you.
All right, so the next portion of that I'd like to talk about is a little bit of, we're going to get into the, you know, what the sensor is able to detect and how and that sort of thing. But I wanted to go into a little bit of what spectrum looks like typically on the cellular side. So I know this is a pretty busy picture up there, and you know, pardon me, but I wasn't able to create all of these slides on my own, so I had to borrow them from various places. But as you can see, this is a snapshot of some cellular spectrum from about 1800 megahertz to 1920 megahertz. And what it's showing is sort of a typical layout of a bunch of different channels and different technologies within the spectrum. So on the far left-hand side, you can see, you know, what's labeled GSM. So GSM typically, well, is a sort of pulsed type of time division multiplexed transmission method where each carrier is only about 200 kilohertz wide, so fairly narrow band, and those narrow band pulses are typically picked up by the wideband receivers on the cell board I mentioned earlier. And then conversely, as we go to the right, we see some, you know, LTE signals. So these LTE signals are very wide band, up to 20 megahertz wide, and they basically are cut up into, you know, many different subcarriers, which all contain different bits of information from different phones. So given that, you know, the LTE spectrum kind of looks like noise from certain perspectives until we start doing demodulation and decoding, then we're really... Okay, thanks, Brad. Vic's going to fix that. Just trying to get back to full screen here.
Why is it not working?
This is why I'm letting Vic drive, because he's the expert using GoTo. So while he's fixing that, oh, that's almost there. So while he's fixing that, I can describe a little bit more about the LTE stuff. So the LTE is just basically a wideband signal that we're trying to extract different pieces of information out of. So we typically use the narrowband scanning receivers for that. One, because the narrow bands can rapidly hop around within that spectrum looking for signals, and two, because they're more sensitive than the wideband receivers. The wideband receivers are very good for picking up the narrowband signals like GSM, which have a tendency to hop around very, very quickly. So we can't follow it quickly enough, but we can follow it, or we can basically detect it with the wideband receivers. And then as you go even further to the right, there's some signals there that look, kind of square, but they're also much, much narrower than the GSM signals. Vic's scratching his head right now. And those ones are typically going to be like the wideband CDMA signals, which are only 5 megahertz wide. And then CDMA, conversely, is also just 1.25 megahertz wide. So we do the same thing with the narrowband receivers there. We basically look, at a portion of the screen or a portion of the spectrum and try to get energy from that particular portion of the spectrum. So you can see below I put in a couple of little notes that, the wideband receiver basically is looking at that whole thing all at the same time, but it has, limited capabilities, and that can only tune to the strongest frequency at any one given point in time. So given that GSM is stronger, it'll tune into those and give you information on the GSM calls. The narrowband scanning receiver, on the other hand, as you can see below, is a much, much narrower little piece of the pie, and we can only basically, with each receiver, listen to one frequency at a time. So we basically scan through and hop through a sequence of channels, maybe from left to right type of thing, in order to detect the different energy at different frequencies. So as you can tell, I mean, we're not listening to everything all at the same time, but so our things like probability of detection is not 100%, but it's somewhere less than that, because we can't hear everything all at the same time, and that sort of thing. So just a quick overview of GSM. As I said, it's a fairly narrow bandwidth, only 200 kilohertz wide, but it's basically transmitted as a series of modulated pulses, with each pulse being about 4.6 milliseconds apart, with a width of about half a millisecond for each time slot that's within the GSM frame. So this is typically the kind of thing we'd see on coming out of the sensor. So we have to sort of take all that information, put it all together, and then feed it up to Zone Defense. And then on CDMA and WCDMA, I've shown a little bit of a spectrum snapshot here, where you've basically got the band in use. So this one's about, this is a WCDMA signal you can see here, which is about 5 megahertz wide. 5 megahertz includes what are called the guard bands, where there should be limited signal or no signal coming out of that particular transmitter. And we use the narrowband receivers for detecting that stuff. LTE is quite a bit more complex than either GSM or CDMA, WCDMA, in that LTE channels can be up to 20 megahertz wide, starting at 1.4 megahertz, and each of those channels is then cut into multiple resource blocks, which are then subdivided down into and allocated to a particular handset. So one handset might get one resource block and at a particular point of time. Another handset might get another resource block and at another particular point in time. So all the handsets can be transmitting at the same time, but they're all sharing the spectrum width of the entire channel, even though we could go down and look at individual resource blocks if we wanted to. CDMA and WCDMA, on the other hand, use spread spectrum to modulate the signals. So basically, each signal is overlaid on top of the other ones. So multiple phones, 64 or 128, whatever the number is, can use exactly the same channel, exactly the same frequency space from, the entire 5 megahertz frequency space, but they're coded such that the base station can pull them out correctly. So some of our cellular limitations include, we don't do anything like demodulation or decoding. Originally, we were asked not to do that, and it complicates the design of the sensor incredibly. And also, given that there's a lot of security on WCDMA, CDMA, GSM, and LTE, that we'd have to get either carrier cooperation for, or figure out a way to decode the different modulation keys. It's extremely difficult to do. Now, some of the other limitations we have in that, as I said before, it's a scanning architecture on the narrowband side. So we can only look at one, fairly narrow frequency set at a time. And we have to jump around in frequency, and basically we hop from channel to channel looking for RF activity on those individual channels. So the more channels you have in the various profiles that get sent down from zone defense, the less time you get to spend listening to each of those channels. And that means that, if there's a very short burst on a channel and you don't happen to be there at that time, you're going to miss it. Things like voice calls, which tend to go on for a long time, typically we'll have a profile where we can detect those more easily. And, obviously things like signal strength is very important as well. Things like CDMA and WCDMA, since they use this spread spectrum technology to spread a very narrow spectrum into a very wide spectrum, it has the effect of lowering the overall signal level, and potentially even the signal can become below the native noise floor of the band, which basically makes it impossible for us to pull out. Also on the cellular side, we have a limited bandwidth, so we can only detect up to about an 800 kilohertz chunk at a time, which is substantially less than a WCDMA channel, and even worse for an LTE channel, which can go up to 20 megahertz. And because we can't do any demodulation or decoding, at this time we can't discriminate between multiple concurrent calls. So at least at the sensor level, there is technology that's being implemented at the software level to attempt to recover multiple concurrent calls at that level.
Sorry, we're just going to take a moment here. I'm going to introduce Shirish. We're going to be, he's going to be discussing some stuff about the travel. So just, I'm going to open it up. I'm going to open up all, unmute. Shirish, you should now be on. Shirish is our VP of Customer Service and QA. Shirish, you're up.
Gentlemen, welcome to the training program. Just a few housekeeping things that we need to get out of the way. The on-site. All right, so I'll continue. So the on-site portion of the training is going to happen at the Executive Plaza Hotel and Conference Center. You guys should have received a hotel block sheet. My request is that you guys make the reservations immediately, as in today if you can, because the hotel is running extremely full. I would also like all of you to reply to, or at least all those who are attending on site, to reply to Victor's email of yesterday confirming your arrival dates and so on and so forth. Right now we have a room block of somewhere between 10 and 15 rooms, so you guys can be comfortable have the conference right there, have the training sessions right there. Both Vic and I will be on site and running most of these sessions. So any questions, technical or otherwise, please feel free to reach out to either of us. That's it.
Thanks, Sharish.
Thanks, Sharish.
All right, we're going to continue.
Thank you.
Sorry, is there a question out there?
And you remember, all of this is fairly high level. We're just trying to go through things fairly quickly to give you a taste of what the sensor is and what it can do. And yeah, the on-site training will expand and it'll be much easier to answer questions as they arise, which I'm sure they will during the on-site training. So, you know, again, I don't know how much you guys all know about Wi-Fi spectrum and cellular spectrum, but I wanted to give you a little bit of a background to it all. So on the Wi-Fi side of things, there's basically two bands, 2.4 gigahertz and 5 gigahertz. Shown here is sort of the 2.4 gigahertz spectrum. You've probably heard that in North America there are 11 channels. There's actually 14 channels defined in the entirety of that band. However, North America FCC has dictated that there's only 11 valid channels that can be used in the U.S. And as you can see here, actually the channels overlap. There's actually only 3 non-overlapping channels within the 2.4 gigahertz spectrum, 1, 6, and 11. So having something on channel 2 and something on channel 1, they'll both interfere with each other and that sort of thing. But we do, on the Wi-Fi board itself, we scan through each of those channels looking for the various packets that are being transmitted by the laptops, cell phones, access points, all of that kind of stuff. We do a lot of analysis of the packets on the sensor itself and send back summary information up to Zone Defense. The 5 gigahertz spectrum gets a little bit crazier in that there are, like as it says here, there's 21 non-overlapping channels, but each of those channels is only 20 megahertz wide. With some of the newer technologies, there's the ability to start aggregating channels together to create 40 megahertz channels and 80 megahertz channels and that sort of thing. This slide basically shows the where the spectrum is, 5.15, 5.35, all the way up to 5.825. Some people actually call this 2 bands, but I typically call it just a single band, so that we say that our sensor supports both bands. So as I said before, on Wi-Fi detection, we support 2.4 gigahertz and 5 gigahertz bands. We support detecting 802.11a, b, g, and n traffic right now. As I said earlier on, we use a off-the-shelf Wi-Fi card from Compex, and using the various Linux tools that are available, turn that into a monitor mode card in order to extract the raw packetized data. So we do things like extracting the MAC address of the device, the RSSI, which is the received signal strength indicator, and many other pieces of information that are available in the clear from the packet header and that sort of thing. Right now we have some limitations on the Wi-Fi side in that we have no 802.11ac support. And again, because this is a scanning architecture, as we're jumping from channel to channel, if we're on channel 1, obviously we're not hearing anything that's happening on channel 6, and so on. So, we don't hear everything all the time, and we may miss things from time to time. But overall, we've got a very good probability of detection. I don't have the numbers in front of me, but Wi-Fi tends to be pretty good because we do have access to the 802.11 header that we are actually demodulating and decoding. Now, as you know, we also detect Bluetooth. Here's a little snapshot of the Bluetooth spectrum overlaid with the 2.4 gigahertz Wi-Fi, and also Zigbee is also in there. So you can see that this is a very, very busy spectrum, and that the Bluetooth channels, which are 1 megahertz wide, 2 megahertz wide in some situations, all must coexist with the Wi-Fi that's there, and any other devices that are in Bluetooth or in the 2.4 gigahertz band, which includes microwave ovens, a lot of phones, like just desk phones and that sort of thing, wireless desk phones and that sort of thing, as well as video systems potentially as well. So there's potentially a lot of interference there, but our sensor is able to pick up both Bluetooth as well as Wi-Fi simultaneously. So on the Bluetooth side, we support monitoring BLE advertising channels, the Bluetooth Low Energy, which is a portion of Bluetooth 4, and Bluetooth Classic packets, which are supported from version 1 and up. On the limitation sides of Bluetooth, we don't tend to get all the information from Bluetooth. It's just really difficult to get the full things like the Bluetooth address. Like with Wi-Fi, we get the full MAC address of the device. But with Bluetooth, because of the way the system's been implemented, it's really difficult to get. So we don't always get that. We get a portion of it, which is enough to allow us to show unique devices in zone defense. And then when what's called a piconet is formed, when you have like your phone and your headset, your phone and your car. Thanks, Vic. And the piconets, we would like to discriminate between which one's the master and slave, but we can't in all situations. So that's another minor limitation. And also, Bluetooth is a very frequency spectrum intense in that it hops pretty much every, how long? Every couple hundred microseconds, 1600 microseconds, I think it hops to the next channel. So it's bouncing around very quickly, and we just can't follow the entire conversation that's occurring. I wanted to talk a little bit about propagation as we're getting closer to the end. So between a transmitter and a receiver, obviously there's a signal that goes across, and with clear line of sight, there's what's called the free space loss, and that's actually directly proportional to 1 over r squared. So the longer the distance, the received signal strength goes way, way down. So here we've got alpha of 2 on the side indicates free space. So in free space with an alpha of 2, so the one alpha is essentially the value that you apply to the distance. So distance squared would be alpha equal to 2. And you can see that given a certain signal in, that the alpha of 2, depending on the distance, the RSSI drops with 1 over r squared. If we change the alpha factor, which you'll be hearing about in the zone defense stuff quite a bit, then the curve changes and the signal strength drops even more dramatically. Even though it's the same signal out, the alpha factor, which is kind of dependent upon whether you're in free space or whether you're in in an office situation where we change the alpha factor because of all the interfering signals and attenuating materials, we basically say that alpha changes based on the particular environment that you're in. So you can see from this slide that it's very highly related to the alpha factor. So a little bit more introduction to RF propagation. This is on the outside situation. So we have a base station that's transmitting to a cell phone, and there's the direct path in this slide that's shown through the trees. So the trees will add some attenuation, and that all adds up to creating the path loss for that particular signal. Now we also have things like the buildings, which are causing reflections of the signal, as well as the potential for diffraction off of devices, buildings, whatever that are within the realm of the wavelength of the signal. And all of those three different paths contribute to multipath. So there's three different signals or more that all arrive at the phone. And the phone has to figure out which one's the correct one. And you know, conversely, if you think about the base station as being one of our sensors, and then the phone being the transmitter, you know, you've got the same thing where you've got the path loss from the phone back up to the sensor, the reflections off the buildings or walls, and you know, the attenuation through walls and that sort of thing. So on the indoor side of things, you know, we've got similar sort of concepts where we've got the transmitter and receiver. We've got, you know, reflections off of walls. We've got diffraction around corners. We've got the direct path through a wall. So all of these different things add up to change the signal strength at the receiver. And because our sensor is specifically looking for the energy of a signal, you know, all of these different things within a site can affect how much energy the receiver receives. And so things like that wall being there, you know, could have a major effect on attenuation. You know, if the wall is thick enough and made of a RF dense enough material, it could be that the reflected path has a stronger signal strength than the direct path. So all of these different things add up to affect the RSSI that's detected by the sensor, and that RSSI signal is fundamentally then fed into the positioning engine to determine where a device is. So as you can see, there's a lot of variables just at the propagation level. I wanted to spend a bit of time talking about antennas. You know, we had the question earlier about the internal antennas and how they're affecting things. So this is sort of a typical omnidirectional antenna, the standard whip antenna that we had on the old sensors, the 3000 series sensors. Standard antennas you see on Wi-Fi access points and that sort of thing. And they'll be called omnidirectional, but they're not truly omnidirectional in that they do have some gain as well as a bit of a pattern to them. So a truly omnidirectional antenna would be a spherical pattern. But this one has a very nice round azimuth pattern, but the elevation pattern is not so good. So in the situation where we're using these kind of antennas on the sensor before, it's possible that, you know, standing directly below the antenna or below the sensor might have perturbed the received RSSI quite a bit based on the antenna radiation pattern. Now this is the kind of antenna we're using inside the sensor now, and as you can see, it's omnidirectional in that it's receiving signals from all directions, but it's not as uniform as we'd like it to be. But you can see that the sort of the front side is much more uniform than the back side. So we're trying to, and it's also completely dependent on frequency as well. So there's no silver bullet for antennas, but we're trying to get the best performance we can with what's available. Going forward, we're going to try and improve this, obviously, but for now, we do have some situations and some frequencies that will perform better than others. Lastly, on the antenna side of things, I wanted to show what a typical cell phone antenna would look like. Sort of a little patch or a little raised device within the cell phone itself. And, you know, typical radiation patterns for a device like this would be these three blobs down below. So you can see there's a lot of variation in that. So the direction of how people are holding the cell phone, you know, whether it's beside their head or not, are all going to affect the radiation pattern and ultimately the RSSI that's received at the sensor, which is key to our current positioning algorithm.
All right, at this point, we're just going to open it up for some more quick questions. Opening it up now.
Any questions?
Actually, I do have one. Just from the mounting method, it kind of just popped in my head, but showing that the azimuth pattern from the new PCB antennas.
Yep.
The potential that it would be best to mount on the exterior walls and then on the interior of the system to mount on the ceiling. Would that be best performance from our solution? Do you guys think?
Possibly. I mean, there's so many variables. It's not funny. I mean, it's the variables of the internals of the sensor. It's the variables of the what you're mounting it to. I mean, there's all sorts of different things that can affect things, but we are still doing some further analysis of this, and it's a long process to determine which is the best way to mount things. But hopefully in the near future we'll have some more information on that for you.
And it's also important to remember that when you're doing the install on sites, that a bit of a site survey is done, just to figure out the best place for the sensors, and that might require doing some actual sensor installation sensor testing while you're there, just to see if having it on the ceiling or on the wall is the best position for that sensor.
Yeah, makes sense. Perfect.
Anything else?
All right, moving along. Oh, all right, moving along.
All right, I see we've got about 5 minutes left. I've got a whole bunch more slides to go through. I think we'll have to skip a few of those. So you've probably all seen a 4000 SE. Power, as you know, can either be from an external power cube or via PoE. And I think Vic probably went over some of that last week in his presentation as well. Oh, he can't remember. That's good. Yeah, so as I said before, we support 802.3 AF PoE going into the master port. And then if you want to daisy chain these things, you have to use passive PoE, going into the master, and then it comes back out the slave, and that sort of thing. Data, again, we have the multiple gigabit Ethernet ports, master and slave again. Similar connectivity, well, the same connectivity for the daisy chain mode, obviously. Master in, slave out to the next one. We also, as was mentioned earlier, we have the PSK product coming out. The PSK will support backhaul 802.11 mesh, and the target is up to 20 units, can all be meshed together, and then go back to a router or directly back to a NUC running the zone defense code. Don't want to talk too much about the mesh stuff here. I think we'll go into more detail when we're in person, but if mesh networking is pretty well known, and we're just testing the alpha of the mesh 2.0 system, and things are looking good so far. But we'll move on. Daisy chain details. I mentioned that we can have up to 4 units per daisy chain. The type of injector you have will determine how much you can actually support on that. Mounting's fairly straightforward. The sensor mounting plate is designed to fit over a standard junction box. So if you have your cables coming out of a standard junction box, the mounting plate can slide on there and be screwed in, and then the sensor will slide onto the mounting plate and be secured with a single screw that could be a tamper-resistant screw rather than a Phillips, as is shown here. We've got some other options coming up. I don't want to talk about these too much in that some of this stuff is just on the forefront of being done. Is the weatherproof sensor where we've designed it to add a gasket around the side to ensure that water doesn't get in. You can see the gasket in the middle and the new mounting plate. We also have the option for a low profile mount. Basically this is better shown in the next slide, where we've created this low profile mount that mounts through something like a ceiling tile, and then the sensor kind of snaps into it from over top. So that's an up and coming option, but not quite ready for release yet. And that's it for now. Sorry for running through the last few slides. I hope that everybody got something out of this. I think Vic's going to take over now and see if there's any more questions we can answer before we wrap it up.
Yep. Thanks, Tim. So just to give everybody another heads up, we are recording this session, so it will be available for later viewing. We'll try and clean it up a bit to get rid of some of the pauses and all that kind of stuff. But we'll open up the floor right now for some questions. And also another reminder that if you haven't booked your hotel room, you may not be able to get it booked in that same hotel. So let's make sure that you guys do that if you're coming on site. And if we can get those numbers and confirmations of who's booked the sites, please, booked the hotel room, please send that my way or Sharisha's way as soon as possible. All right, opening up the floor to questions.
Only question from my perspective is for all the meetings, do we have a GoToMeeting set up for all the presentations and training and all that?
Yes, those have already been sent out for the online training. We're working on getting some recording done for the on-site training, but again, the on-site training is what it is. It's on-site training. It's going to be hard to duplicate remotely.
No, definitely. Sounds good.
All right, well, I guess there's no more questions. Once again, guys, thank you for your time. If there is any questions that you guys can think of, feel free to send it my way. I'll include Tim's email address as well. You can bug him. All right, guys, thank you very much.
Thanks, guys.
Thank you, guys.